All right, in Unit 4, we continued talking about dynamics, but in this case, we were starting to talk about circular forces instead of linear forces. So recall our steps to all of our Newton's law of problems. The first thing that we would do is we would draw a good free body diagram showing all of the forces that were acting on an object, and then we would ask ourselves, is this object accelerating? Right? So for circles, the answer to, is this object accelerating is yes, it always is accelerating, because when something's going in a circle, it's always going to be turning. So even if the instantaneous speed of the object, or the speed of the object at every moment is staying the same, we still say that the object is accelerating because it is turning. So remember, acceleration is your change in velocity over time, and that can be done by speeding up, slowing down, or changing your direction. So in this unit, we really covered this idea of uniform circular motion. So what uniform meant is that the radius of the rotation is always going to be constant. The mass of the object that was rotating usually stayed constant and stayed the same. And the object was rotating at a constant speed. All right, so let's then go back and address that question again. So is it accelerating? And the answer was yes. So for our Newton's law of problems, the next step for us was to then write a sum of all forces equation. So in terms of linear stuff, we said the sum of all forces, or the net force, is equal to the mass of the system times acceleration. But for circular stuff, where it's going to look a little bit different. So we have the net force still is equal to the m of, instead of the m of the system, we typically refer to this as the m of the rotating object, and then v squared over r, which v squared over r is centripetal acceleration. So this right here, the velocity squared divided by the radius, is known as centripetal acceleration. Right, this is the mass of the rotating object, and then the net force is called centripetal force when we're dealing with circular stuff. But again, we never plug centripetal force really into equation. We're always trying to ask ourselves, based on the free body diagram, where are the arrows pointing? So we're going to look at a free body diagram, and we're going to select the arrows that are pointing straight in or straight out at the point in the path that will contribute to mv squared over r. This could be at an angle as well, but if that was the case, then you'd have to find the components. So let's say we have an example of a stopper going around in a string. Then like at the bottom of the string right here, if this were the radius of the motion of the object, we're going to have a couple of forces acting. We're going to have tension, which would point upwards, and we're going to have force due to gravity, which would point downwards. Right? So these two forces are going to add or subtract in order to equate to the net force that we can set equal to mv squared over r. So when we write our sum of all forces equation, we're always going to start with the force that's pointing towards the center of the circle. All right, because that would be the positive direction, and if we make this positive, which is the direction of the net acceleration and the net force, we have to have them have the same symbol mathematically. So for this, I would always say ft minus fg is equal to mv squared over r at the bottom of the circle. Okay. Now let's kind of go back. I just said like this points in the direction of the acceleration. So if we have an object that's moving in a circular path, the direction of the net force is always going to be towards the center. Right? So here we would have to have the tension force greater than the force due to gravity, which I didn't really draw that very nice. If it wasn't that, then this would actually fly down towards the ground, right? So we have net force pointing towards the center. And so because forces cause accelerations, that means the direction of the acceleration would also be towards the center. And remember that when something's moving in uniform circular motion, that the velocity or the speed is always tangent to the circle at that moment. All right, so this is a tension example. Let's kind of look at some other examples that we've talked about, right? So we did the stopper at the bottom of the string. Now we do the stopper at the top of the string. So in this case, the tension would both be down and the gravity would both be down. right? So here we would have ft plus fg is equal to mv squared over r, and it wouldn't really matter which one we put first since they're both pointing towards the center of the circle. If I had a loop and a roller coaster, or a loop and there was a block going around, I could be at the bottom or at the top of that loop. And at the top, we would have two forces acting down, which would be both gravity and normal force. And then at the bottom, we would have gravity and normal force as well. And again, I'm not drawing these vectors to scale. So if we wanted to do our sum of all forces equations for those problems, we have this, which is Fg plus Fn is equal to mv squared over r, or down here, and again, we want to start with whichever one's pointing towards the middle, so this would be Fn minus Fg is equal to mv squared over r. Oops, I left my r off there. All right. Now, in this instance, when you're at the top, many times you might be asked, and for this one too, what would the minimum velocity be for something to maintain its motion around? And in that case, what ends up happening is as the velocity goes slower and slower and slower as we're trying to hit that minimum value, less and less of the net centripetal force is being caused by either the normal force or tension in these cases until they become zero. And the only thing that's causing you to complete the rotation of the path is gravity. So in that case where you would feel weightless at the top of the circle, or when you just maintain contact, or the minimum possible velocity without something falling, that's when these would approach zero. So we would have this example of mg is equal to mv squared over r, and our m's cancel. So if you're not told mass in these kind of problems, we can still figure those out. All right, so we have a roller coaster that's in a loop, but we also have the roller coaster that could be like this, like you're going in different like over a hill or at the bottom of a hill. And when you're going up over the top of the hill, you start to fly out of your seat and you feel like you're not pushing in so hard. You kind of get that your stomach dropping feeling. But if we draw the free body diagram, we see Fn and Fg pointing in those directions. And here you're right side up too, and we have Fn and Fg. So seemingly these two things look very similar, but we know that it feels very different when you're down at the bottom than when you're at the top of the hill. And the reason is because of where the circle actually is. So this is the rotation right here, and this is the rotation right here. So if I was going to do the sum of all forces equation for this guy, remember I'm going to start with Fn, so I'm going to do Fn minus Fg because it points towards the center, giving Fn and the net force the same direction, or the centripetal force here. And then if I wanted to do this one, because gravity is pointing down towards the center of this circle, then it's going to be Fg minus Fn is equal to mv squared over r. All right, so those are just a few different types of examples of circular motion on string, stoppers, tension, normal force. And then in this unit, we started to talk about really where does that acceleration due to gravity come from, and we talked about the universal gravitation, so the law of universal gravitation. And this is an inverse square law, and we kind of came back to it when we were talking about electricity and comparing this and the electrical force, because they're both field forces. They're the two fundamental forces in the universe in inverse square laws. So the force due to gravity is actually a constant g, the mass of one thing times the mass of the other thing, all over their distance apart squared. And this is really the distance between the centers of mass. And sometimes that is negligible, but sometimes it actually matters. So if I was talking about the Earth-Sun distance, the radii is negligible. So like the radius of the sun and the radius of the Earth are so tiny relative to the distance between the Earth and the sun that it doesn't really matter. But if we were talking about a person standing on the surface of a planet, well, now the person's radius or center of mass, distance of center of mass, really is negligible, but the distance from the center of the planet isn't negligible, but we end up having it be the radii. So if you just remember that this is the distance between the center of mass and sort of keep scale in your head, you can figure out whether or not the radius of the planet is going to be important, or the radius of both objects are going to be important. All right, so this is force due to gravity. Let's put that constant in there. So it's 6.67 times 10 to the negative 11th, and it's meters squared over kilograms squared times newtons, which makes this and this cancel and gets you left with newtons here. Right? So by an inverse square law, we mean that as the distance increases, the force is going to decrease relative to the square. So like if I double the radius, it actually, or the distance, it's actually going to make the force due to gravity 4 times smaller. Whereas it's directly proportional to the product of the masses. So if I double one of the masses, it will double this number. And we've done a lot of that, so I think you kind of have gotten the hang of thinking about things as they change proportion there. All right, so let's kind of derive this out and see how we used it other than just in and of itself, right? So one of the things that we would do is we would say, all right, how do we use this to figure out the acceleration due to gravity on any planet? We know that little g, or acceleration due to gravity on Earth, is 10 meters per second squared, roughly, right? So we've already seen one equation for FG, it's mg, so we sort of plug that in there. So mg is equal to g m1 m2 over r squared. And so I can actually get one of the masses to cancel. And the mass that cancels is like the mass of the person standing on that planet, right? Because we know that mass really doesn't affect acceleration due to gravity. Acceleration due to gravity on any planet is relative to both that planet's mass and that planet's radius. So this is another equation that's good to remember, that acceleration due to gravity on a planet is equal to m over r squared times your gravitational constant. All right, and then the last way that we did it is we treated it as a centripetal force. So if we're talking about the Earth and we have the moon over here and it's going in a circle around the Earth, well, the thing that's actually causing the moon to turn around the Earth is an attraction towards the Earth, which is a force that's towards the center of the circle. So it's a centripetal force. And in this case, it's specifically that force due to gravity. So we can say that Fg is equal to mv squared over r. So we have our universal law of gravitation is equal to mv squared over r, right? Now, one of the m's is going to cancel, and which m is this? Well, this is always the m of the thing that's doing the rotating, right? So that would be the mass of the moon in this case. So we would get one of the masses to cancel. The r's are the same, so we also get one of the r's to cancel. So a lot of times we talk about like the velocity of an orbit based on how far something is from the center of the Earth. So we can get g m over r is equal to v squared. Okay. But again, this equation and this equation are probably not on your reference tables. This one is, but these other two could be easily derived. All right, so that's just a little review of circular forces, and in the next couple of videos, we'll start talking about energy and momentum.